linear algebra, the mathematical concept of bases. Okay, so before we get into the intuition of bases, a basis of a vector space V is mathematically defined as a subset that is both linearly independent but also spans V. So here's our mathematical definition. So what does this really mean? Okay, so let's give some intuition. First of all, a basis is just a bunch of vectors. It's just a set of vectors, but it has some special properties. What are these two special properties? Well, the first is that the vectors need to be linear independent. So we have this set of vectors, and one property this set of vectors has is that they are linearly independent. The second is that this set of vectors that we have spans our vector space. So we have a vector space, we've taken this bunch of vectors. Not only do these bunch of vectors span the vector space that we have, but they also are linearly independent. And when we have this special type of special group of vectors, we call them a basis. So to understand this intuitively, consider again our block of flats analogy. Suppose the vector space we want to find a basis for is one of the floors. For the sake of habit, let's say the vector space is the third floor. So our vector space is the third floor. As usual, we have a bag of instructions, e.g. one instruction might be to walk forward one step, another to walk diagonally to the right one step. It doesn't really matter what those instructions are. So first of all, to consider our basis, we want to be able to get everywhere in our vector space. So we need a bag of instructions or vectors which spans our vector space, right? In other words, a basis in part, the first part of the two-part definition says that our vectors allows us to get everywhere in the vector space. In the context of our analogy, everywhere on the floor. The second property of a basis, linear independence. However, what makes a basis special is that we have a second demand on our set of vectors. Not only do we want them to span our vector space, or in our analogy, not only do we want our bag of instructions to allow us to get everywhere on the third floor, but we also want to make sure that we don't have any superfluous instructions, that we have just enough instructions to get everywhere we want, but no more. How do we work out whether our set or group of instructions is small enough, i.e. has the smallest number of vectors possible? We test for linear independence. Now intuitively, why are those two things the same thing? Why is trying to find the smallest number of vectors in a set the same thing as asking is this set linearly independent? Well, remember, if our vectors are linearly dependent, then at least one of the instructions in the set can be written as a linear combination of the others. Intuitively, what does this mean? So back to our analogy, the vector space we want to span is the third floor. Suppose our set of vectors is walk forward one step, walk to the right one step, and walk diagonally to the right one step. Then this vector is a combination of these two vectors. And actually that's true of this vector. This vector is a combination of these two vectors. Let's see how this is the case. So this vector here is quite clearly this vector plus this vector. But by the same analogy, this vector here is this vector minus this vector, and so on. If you have vectors which don't have this dependency property, i.e. they're linearly independent, then they're the smallest number of vectors you can have. So what's the conclusion? A basis is just a set of vectors, but it's a set of vectors with two special properties. The first is that it spans our vector space, and the second is that the vectors in the basis are linearly independent, i.e. it's the smallest spanning set of vectors for our vector space.